at Columbia University before moving to Colorado, where he founded UNAVCO. In the past few decades, as a professor of geology, there he has applied GPS to the monitoring of processes on most of the plate boundaries of the world, and especially to the Himalaya. Professor Roger Wilhelm operates a creep meter network in California and long baseline tilt meters in Cascadia, Pozzuoli, excuse my pronunciation, and Mexico. Among his 250 publications, there are several highlighting earthquake risk to the cities, especially in developing nations. He has appeared in numerous movies about earthquake and mountain building processes. In 2012, he has the recipient of the American Geophysical Union Witten Medal for Geodesy. Thank you, Professor, for joining us. We may start. Thank you.
Okay. Well, thank you very much for inviting me here. In fact, this investigation of the earthquake has been going on for the past 3 months, as you know, and it hasn't been possible without the graduate students from Yildiz University. I'd like to thank them and those from Kandili who've been participating in this. So we put in 13 instruments, and I'll be telling you about what we found out. I'll also tell you a little bit about what we found out in the last several years from after-slip measurements. So, how's this go? Not moving. I need to advance. Okay, great. Okay, thank you. All right, so this is not going to be another boring talk about artificial intelligence, but it is the application of AI to fault zone studies. And I'm defining AI in this case as actual investigation, meaning that we go out and find out what's going on. So let me just define what the terms of reference here. I think of active faults that have creep in two ways. They either sleeping faults or creeping faults. And there's a distinction between the two in that a sleeping fault is a fault that has an earthquake at depths that drives creep above it to shallow depths, and eventually, if it's big enough, it will reach the surface. It results in, can you see this cursor? Yeah, you can, good. So it either increases the rate of surface creep, or it triggers slip, or it triggers after slip. And sometimes it's possible to get a rupture right to the surface, as we've seen recently. The other type of fault is known as a creeping fault. It's driven by plate boundary shear. So although there's a shear signal occurring in the deep seismogenic zone at the base of this fault, in this case, most of the maximum slip occurs at the surface and penetrates downwards. So there are two different ways of looking at faults. This is driven from below because rupture has started a shear process that drives upwards towards the surface. So you have maximum slip, maximum creep at the base of the creeping zone, the top of the seismogenic zone in violet here. And in this case, you have the opposite, where you have a shear strain. These two arrows indicate a shear strain applied by plate boundary processes, and it produces the opposite. It produces maximum slip at the surface and slip going down to depth. Now, in fact, it's possible that is more interesting than after slip. So in terms of the seismic cycle, just take a look at this for a moment. This is a cartoon of what's happening. Earthquakes occur when strain reaches a certain level, a failure strain, and that introduces slip on a fault. And at seismogenic depths, you just have no slip between earthquakes until the strain arrives at some large value and it causes fracture and slip. The surface fault, however, behaves very differently on a creeping fault. When there's a co-seismic slip episode at the base of the crust, it introduces a delayed afterslip. The amount of slip that actually gets manifest is usually the same, like this might be a meter of slip, and this might be a meter of slip, but instead of being manifest within a few seconds of the earthquake, it is delayed for maybe 3 months or 3 years, or even longer in some cases. And then afterslip is replaced by a slow slip process driven by plate boundary shear, and this interseismic slip creep continues until the next earthquake. It could be linear or it could slow down with time, but eventually the next earthquake will introduce this same afterslip process. Now, we've not actually seen afterslip repeated on any rupture. The Parkfield earthquake has a recurrence interval of about 22 years, and it's the closest we've seen. So we've seen one rupture, but we've never seen two. Never seen two earthquake cycles. That's going to change with time. Creep was only discovered in the 1960s. Could someone tell the machinery to stop operating? Sorry, we got a construction project next door. So I'm going to just give you some terms that you've all heard about. This is the afterslip from an earthquake known as the Superstition Hills Fault earthquake of 1987. And we have 37 years of surface creep following that. The interesting thing about this is that at the time of the earthquake, there was no slip at the surface at all, nothing. So geologists went down there looking for, which fault produced this earthquake yesterday. They drove like crazy to the epicenter and found no cracks at all in the subsurface. All the slip occurred in the 3 years following the earthquake. And now we've got 37 years, we can see the bigger picture unfold. And if you look at this carefully, you can see there are various little jumps in it. And these are known as episodic creep events. Some of the jumps occur at the time of large earthquakes nearby. The Landers earthquake was magnitude 7.3, there was a 7.1 here and a 7.2 here. These three earthquakes all introduce sudden jumps of the fault. And that's known as triggered slip. And it can take as little as a few minutes, or it can take as long as a couple of weeks. I'm going to give you an example of that happening at İzmit Pasha on the North Anatolian Fault in response to the Kahramanmaraş events. So that's triggered slip. Episodic creep events, I'll show you some examples of these. These are fascinatingly different. They have a very long response time, maybe with a duration of 2 or 3 weeks. They are multiple events. They travel along the fault in both directions, and they propagate to distances of the order of 10 kilometers. Then between all these jumps, you have steady creep on the fault. Steady creep can occur as slow as a 0.1 millimeters a year. It's really almost impossible to see because it's close to the noise level of ground motions. But in this case, it's about half a millimeter per year. So afterslip is over in about 3 years. You can see 1990 to 1995, most of the afterslip is over. It may continue to 2000 here, and then it's replaced by linear slip interrupted by these creep events. Now, creep events are, in fact, interesting for this reason. A creep event is a small earthquake, and since it happens repeatedly, one can focus research projects at how the process works. And that, I'm afraid, has not been done much in the past 50 years. People have taken creep events and said, well, it's just fault slipping in its mud. It's got nothing to, it has no relevance to a major earthquake. But I think they're wrong. I think that we can learn a lot from studying creep events, and I'm going to talk about that quite a lot in this talk. So moving on, onwards, I need to go this way. Here is a creep event on the Superstition Hills fault, the fault we were just looking at, that happened last week. In fact, it happened between the 15th or the 16th of May, and it's still ongoing, right? And it's this black line, and you can see the creep event has a duration of about 2 weeks, and it's made of multiple events. Each event has an amplitude. In this case, the largest is about 10 millimeters. It's followed by events with 3 millimeters, 2 millimeters, and so on. But what I'm showing here are 2 creep events about 20 years apart on the fault, 2006 to 17 years apart. They're effectively very similar. And that's why the study of these processes, which we can get at very easily by putting surface measurements, is going to be interesting in the future. I think it's a promising research direction. And since you have these wonderful creeping faults in Turkey, you should devote some time to their study. They're equivalent to magnitude 4.5 earthquakes. They're, in other words, they're not dangerous. They're not very important. How do we calculate the magnitude? Very simple. We take the slip and the area of the fault, the area being the length and depth. The depth is usually about 3 kilometers. The length may be 10 kilometers. You simply multiply you obtain the area and multiply it by the slip and the rigidity modulus, and you come up with a magnitude of the order of 4.5. These are quite large creep events. Most creep events are small. Okay, it's decided to not go forwards or backwards. What did I do? Thank you. Now, triggered slip, I mentioned this. This is when the fault slips in response to a nearby earthquake, a large earthquake, a magnitude 7 or greater, or it could be a magnitude 8 at 1,000 kilometers. We've seen triggering. And in this case, it's the same fault as you've just seen, but the slip occurs between 2 data points, 15 minutes apart. Now, we've stopped measuring at 15-minute intervals. We now record 1-minute intervals because we're interested to know how fast these events really occur. Well, one clue came from this earthquake. The array of GPS receivers surrounding the fault at Aseismic Pasha recorded the slip in 2 minutes, about 2 minutes at the time of the S wave. And I'll show you the response from the creep meters was nothing like a 2-minute response. If you look at this, you can see I'm plotting about a month of data from February to, sorry, I'm showing the first few hours. Sorry, this is in hours. I'll show a longer record in a minute. But this was not this. You can see the 2 earthquakes, the 7.8 and the 7.5. The 7.8 triggered the same amplitude creep event as the 7.5. And what is interesting is the duration of the slip event was about 6 or 7 hours, in this case, interrupted by another 6 or 7 hour event that triggered by the 7.5. And the amplitude was about 1.2 millimeters for each of them. So what's odd about this is that the GPS result showed a full 8 millimeters occurring at presumably at depths of the order of probably 3 to 5 kilometers, whereas the creep that occurred on the surface, as you can see, recorded by these 3 creep meters near each other, within a kilometer of each other, that was not triggered by the S wave, but by the surface wave, and it took several minutes. Okay, so what I was showing you just now was the initial triggering of that event. And over the next 2 months, this 40 days in this case I'm showing, you can see there was the initial triggering on the fault, that is Aseismic Pasha, followed about 2 weeks later by another creep event that brought the total slip up to 6 millimeters. Actually, this is extension. You have to multiply by a calibration factor to get the true slip, but the true slip is about 7 millimeters. So what took 2 minutes at depth took 40 days at the surface. So this is an important property of creep. It follows slip at depth. It does not precede it. People, when they first discovered creep, they thought, aha, maybe if we measure creep, we can watch earthquakes approaching and have some kind of warning system. But it seems that creep does not signify something happening. It signifies that something has happened in the past. It follows creep. So it's not that useful. The typical creep event at Aseismic Pasha looks completely different from this, with one exception. The individual slip events that occurred during the creep event episode at Aseismic Pasha are about the same amplitude as that from a spontaneous creep event of the sort that happened in 2019. And you can see 1, 2, 3, 4, 5 creep meters here, all recording different amounts of creep. And you can identify individual creep events that are small at some sites and large at others. And you can measure the propagation direction and velocity of these sub-events. And I think I show that in the next picture. Okay, this is just a more detailed version of this triggered slip at Aseismic Pasha. The initial triggering at the time of the surface wave arrivals, the Love wave and the Rayleigh wave, followed by this second event. And you can see there's a delay. In other words, the slip in the second event is propagating along the fault. In this case, it's propagating to the east. The blue picture here is the rainfall record for this period of time. It was started during a period of snow, and in fact the snow covered the solar panels and shut down the instruments for part of the time. So the data are a little bit fragmentary. Sorry, it won't advance. Okay, here is an analysis of that 2019 creep event, and I'm showing the creep event recorded by 3 creep meters at different locations. I'm afraid that went forward on its own. I don't know, it's gone into a very strange state. Nope. I'm in an edit mode. How do I get out of that? Sorry about this.
It should be transferred this maybe.
So we have a little technical hitch here.
Does it work now?
I don't know what it's doing. Okay, that was the one.
This one?
Yeah.
Okay. You can use this.
Oh, okay. All right, got it. So here is this complex creep event that happened in December 2019, recorded on 3 creep meters, and the bars indicate the eastward propagation velocity for individual creep events. And you can see the velocity varies from, okay, you can see it varies from less than half a meter per second, this small value, to a rate of about 2.5 meters per second. So you've got to imagine now the fault is locked, and then this little pulse travels eastward along the fault, allowing a small amount of slip. In this case, this one traveled at 2.5 meters per second and permitted about 1 millimeter of slip. These are very small amounts. And of course, they're invisible to both seismometers and GPS. It's too small for GPS, too fast for GPS, and too slow for seismometers. So this is applying creep meters like this gives you a window into a completely different way of looking at faults. Okay, yes, no. Okay, all right. So I'm going to now ask some, I'm going to move away from the observations briefly. I can't operate this computer. I'm sorry. It doesn't do anything what I want. Ah, that's what I want. Perhaps you can operate this for me. So some interesting questions arise. You know, why do faults creep? Do fluids play a role in either enhancing or initiating creep, or slowing creep down or speeding it up? Why is surface slip delayed compared to seismic slip at depth? And what fault zone processes can we measure on the surface fault that haven't yet been measured? Because there's a lot going on, and we simply have been using creep meters in a very silly way. Next slide. That's going the wrong direction. Okay, good. So the first thing we could ask is, are there fluids in the fault zone that as they make their way to the surface become gases, like carbon dioxide at a depth of a few kilometers that under such a high pressure that it's a liquid, and that it actually lubricates faults? And Irwin and Barnes in 1980 wrote a really important paper, which I recommend you read. And they pointed out that most of the world's fault zones are regions where CO2 emanations from the subsurface are pretty intense. So they're looking at a worldwide association between carbon dioxide coming out of the ground and faults, active faults. And they basically argued the reason is that changes of stress and strain in the fault zone are causing a rearrangement of channels that vent gas from depth towards the surface. And they even went as, or rather, Jim Rice did a very careful study to try to look at this analytically, and he pointed out, or came to the conclusion, that surges of poor pressures could slowly make their way up a fault zone. So can we do that? Can we measure fault zone processes? So this is a study by Kennedy et al. In 1997, and the picture on the left shows the Parkfield region and the rest of the San Andreas Fault and as a series of boreholes. And why the geochemists use boreholes is, of course, that a borehole extracts gas from depth directly, so you know where it's coming from. And they found that there was not only a high level of CO2, but also a high level of helium-3, which must be coming out of the mantle because it's not found naturally in the crust. So the problem with boreholes, of course, is that they are they're never actually located on a fault. They're usually to one side or the other. And so that's not particularly useful result. The most exciting moment for me was seeing this picture. It was a movie taken by your geologists of the Sivrice earthquake, of gases coming out from the Euphrates, and they're coming out of a fracture system, which you can clearly see is an en echelon shear zone for a left lateral fault. And the gases sort of died down after about 3 days, but it raises several interesting questions. Does gas also come out of the fault during creep events? Does gas facilitate creep? Does the fluid and gas in the fault zone reduce the friction and allow a creep event to occur? Do earthquakes release gas through metamorphic processes? And more importantly, is it possible that new metamorphic processes releasing gas actually initiate ruptures at depth. So this is pretty interesting stuff. So the question is, how do we measure it in a fault zone? Well, here are three things. The one on the left is what the geochemists use, and in fact, the two on the left they use. I don't know how they are satisfied by the uncertainties in this kind of measurement. You can see it's a tube that's dug into the ground, only a meter or so it's very shallow gas. And in this, the left-hand one shows merely gases being extracted and analyzed. So you're attempting to get the ratio of different types of gas. So you could be looking at noble gases like xenon and argon and so on, and comparing that to the ratio of CO2. It doesn't tell you anything about the volume of gas coming out. To do that, the geochemists use a thing called an accumulation chamber, and they place basically a bowl facing downwards on the Earth's surface and allow gases to get into that hemispherical bowl, and then they pump the gas from the top of it through a detection system and back into it, and they assume that the gas is diffusing as a function of time. To me, these are very unsatisfactory ways of measuring gas, but I haven't managed anything better. The one on the right is what we use. Essentially, it's the accumulation chamber at the bottom of a 1 meter deep pit. We suck the gas from the top of it through a detector that detects carbon dioxide or hydrogen or methane or radon, and we vent it out to the surface. So these things cost about $300 to make. So they're not expensive, but the problem with them is you need to deploy many, many sensors to make sense of what's coming out of the ground. Next. Here's an example. What you're looking at is a red line that starts on the bottom left and goes to the top right. That's creep from 2 creep meters. And during this interval of time, it's about 2 years during the pandemic. This is what I did in the pandemic. It's really interesting, by the way. I think pandemics should happen all the time because you can go off and do fantastic science without anyone bothering you. Sorry. So the top green line is the concentration of radon during this 2-year period. And the bottom blue is the concentration of carbon dioxide. And you can see they're roughly the same. There are points where the data are not working. The radon instrument got flooded, for example, and we had to put a new one in. But essentially, they do the same thing. And the reason is that radon, it acts as a kind of passenger on a train, and the train is the carbon dioxide coming out of the ground, and the radon is sort of blown out of the ground by this venting of the CO2. And I'm showing you this one because it's typical of many that we have. I had to put about 20 of these things in. And okay, what's the important thing here? First of all, the amount of gas is enormous, okay? The concentration of radon reaches 100 picocuries per liter, okay? Then it goes off scale. Okay, the safe limit for gas radon in a house is 4. This is 25 times higher than the safe level. So, you know, if you're near a fault zone, don't camp on it because you will wake up with 4 noses or something through mutations. So that's the first thing. The radon level is really high, and so is the carbon dioxide level. Notice it goes off scale at 4,000 parts per million. Atmospheric carbon is 400. So it's 10 times the atmospheric carbon level. So there's a lot of gas coming out of this. The third thing to notice is that there are creep events here. There's one, one here, one here, one here, and one here. You can see the jumps. These are creep events. You'll notice that there are spikes in the gas emanation coming out a few days after each creep event. Okay. In other words, yes, creep events do vent gas. We don't know whether they cause the creep event or whether they are caused by the creep event. But it seems that there may be some useful research direction there. There is also one problem thing, this one here. Can you point that one up? It says desiccation and formation of on echelon cracks. So here's a peak in both carbon dioxide and radon that does not correspond to a creep event. What's going on here? What I think is happening is the ground, which is clay, is drying and a crack is propagating downwards and it taps underground gas, which vents out at this point. So here's a problem with the measurement system that can throw you off. Next. Okay. Another interesting thing happening. What I've done here is I've stacked the carbon dioxide concentration measured each minute for an hour. 20 minutes, 10 minutes on each side of the creep event. And I'm showing the red line shows the opening rate of the fault. The fault opens during the creep event. And you'll notice that there's a decrease in carbon dioxide just at the time. Yes, thanks, Celia. That just at the time of the creep event, the carbon dioxide level goes down. This seems to be the opposite of what I've just said. But what is actually happening is the fault zone is opening, and as it opens, it sucks in atmospheric air, which of course is only 40 parts per million. So the concentration you can see on the side is 700 parts per million. In other words, the dilation of the fault actually is the fault zone breathing in atmospheric air during the creep event. Next. So how fast does this gas come from the surface, or from the seismogenic zone to the surface, if that's where it's coming from? Well, the bottom picture shows a roughly 30-kilometer distance from left to right. And you can see blue dots and green dots and red dots. Those are micro earthquakes at depths of 8 to 10 kilometers. And as you can see, they propagate southwards, and they take several weeks to do so. The plot on the left, the blue ones on the left are in March, the red ones are in June, and the green ones are in August. So this is a sequence of micro earthquakes propagating along the fault. Now, at the same time, we saw gas coming out of the fault a few weeks after the seismicity passed beneath. So the red dot seismicity resulted in a gas burst about a week later. Oh, so wait a minute, have I got the times right? No, the velocity calculated from this was about 1 kilometer per week, which is pretty slow compared to the creep propagation velocity, which is more like 2 meters per second. Okay, and the gas is propagating at about 6 meters per hour. But it's kind of interesting, and the question is this really what's going on? Is gas being produced by the earthquakes, propagating slowly to the surface and then venting at the surface? Or is a carbon dioxide fluid burst triggering the seismicity? And that's a question the experiments that we've done so far can't answer. One other thing. It turns out that these ants, these wood ants in Europe, like building their nests on fault zones. And nobody really understands why they do it, but it turns out that they're 8 times more likely to establish a colony of these ants on top of a fault, not even an active fault, it's just a passive geological fault, meaning that there are indeed reasons for the ants doing this. And it's probably that they like some combination of the gases. They think this is a good place to build their nest. Next. Okay, now moving on to another way of looking at creep. The picture on the left shows the standard way of measuring creep on a fault, you put in the black arrow is the creep meter. And when this fault, this is a dextral fault, when the fault moves, the creep meter is extended, and the creep value is given by the ratio of the extension divided by the obliquity, the cosine of the obliquity. Now, the problem with this is that you can't distinguish between the fault opening and the fault sliding. If this were a normal fault, okay, what you would measure would be just the normal fault component. So we ask the question, do faults simply slide, or do they open when they slide, or do they close? So we introduced a few creep meters like the one in the middle that have two components. They have the first component that measures oblique slip, and they also have, it's great, thank you, Seth. They have a measurement, an instrument that measures the dilatation too. And suddenly we have a new window on what's going on. It turns out that when faults slip, they open. At least most of them do. And I'll show you some examples in a minute. What we're working on now is a completely new type of instrument, which has multiple sensors that measures the arctan of the deformation field directly. In other words, there's no ambiguities and no complicated trigonometry to determine what's going on. Next. So let's have a look at a measurement. So this is one fault. It's the San Andreas fault again. Previous picture. It's a picture of the San Andreas fault. Not working. Oh dear. Technical difficulties. But what I'm going to plot is the, can you go back one? Yeah. Yes, okay. The orthogonal component is on the left. It doesn't want to. And the dextral component is along the bottom. And so what I'm doing is plotting the vector of slip across the fault. If you can't get back, well, let's look at this one. Here's a series of, oh, yes, yeah, stop. Okay, so the circles show measurements made once per hour. So where there are red lines with a wide spacing of red dots or red circles, the fault is slipping quickly. Those are creep events. So during a creep event, the fault opens, the orthogonal component opens 0.15 millimeters, and the slip on the fault is about 3 millimeters, dextral slip. And then you'll see a very thick red line, that's millions of little red dots waiting for the next creep event, which might be in 4 months' time. So each of these ups and downs takes either about 6 hours or 4 months. So 6 hours opening, 4 months closing, 6 hours opening, 4 months closing. You get the idea? So what's happening here? The fault is dilating as it slips. It means that usually when you have a granular material in and you slide it, it will expand. It's called dilatancy. So here is direct evidence of fault dilatancy during the creep process. The fault opens when it slips, and then when it's moving very slowly, it closes. Now, how can we, what does this actually mean? We measured it on a whole bunch of faults, and I'm showing them here. I'm not going to dwell on them because it's irrelevant. But essentially, most faults are opening all the time. There are a few faults. There is one fault shown here that is closing, and it's in a transpessional fault that we know is being squeezed by the San Andreas fault. So most shear zones seem to be opening in the long term. This is a period of 2 years you're looking at. Next. Yeah, I don't like PCs at all. We're stuck. What if I press it?
You can use this one freely. Siz de hocam sadece şu aşağı ok tuşuna basarsanız mesela.
Oh, we've got all sorts of things going on. Okay, next.
Orada mesela.
Next one.
Bekleyip.
Okay. This is a fault, a creep meter across the Dead Sea, and what we're plotting is the same. Vertical is a dilation, so the blue line in the middle is the fault dilating. It's a normal fault, and you can see that it goes both dextral and sinistral during this period of time. There was no slip on this fault, by the way, during no triggered slip during the Kahramanmaraş earthquake. Next. Okay, another thing that we've noticed on faults, nobody likes measuring, people that don't measure creep dismiss it as a noisy measurement because when it rains, you get rubbish. The fault doesn't tell you anything sensible. And what I'm showing here are in red, you see the blue line that's going diagonally from bottom left to top right. That shows creep events in red and inter-event creep in blue. And you can see a rain event at the beginning there where the fault goes backwards. The fault actually, instead of going dextral like the San Andreas should, it goes sinistral for about 4 millimeters. And this, of course, is a very puzzling form of noise that nobody could understand. During each creep event, the picture on the right shows minute values, very rapid dextral slip and dilatation at the same time. That's the process we were looking at. The next picture shows samples of rock from 3 fault zones, the North and East Anatolian fault zones and the San Andreas fault zone. And you can see very similar shaped objects here. They're called clasts or phacoidal clasts. They have polished sides. They're made of clay. They obviously are sliding relative to their neighbors, and most people have not noticed them because when they've put instruments in fault zones, they use backhoes instead of students. But if you get a student to dig a hole, as I have this week, and thank you, FA, you usually find these clasts in the fault zone. In fact, we've been digging largely in rock in the last few weeks, and we haven't discovered many of these. But we now realize that the texture, the foliation in the fault zone is responsible for this strange behavior. Next slide. So we have we've developed a model which shows what's going on. If you have very rapid shear, like in a creep event, applied to these clasts, you rotate them, and in rotating them, you lever the fault apart. It actually pushes the fault zone apart. So this explains why you have dilation during slip. And then during the long period when the fault zone is moving slowly, the friction is insufficient to keep those rotated clasts in position, and they collapse to their former value. And when you have heavy rain, the water in between the pore spaces lubricates the faults, and the fault zone collapses quite rapidly. And it can actually induce what appears to be, due to the rotation of the class, it can produce this apparent backward movement of the fault. So here's a model that explains why you get this erratic behavior of the fault during creep events and during rain. Next. Okay, let's go past this one because I realize we're running out of time. So after slip has manifested itself after a number of earthquakes now. Probably 100 earthquakes have had after slip, and the seismologists have treated after slip as they would an Omori decay law process. And several of the equations that have been designed to emulate after slip, the logarithmic decay with time, have been based on Omori's law. But I'm showing you here 6 different equations, and the problem with them is that none of them work. they're complete rubbish. It's just waste of time trying to apply these things, despite people having spent, there's a lot of literature describing, well, how the afterslip process works. Well, obviously, it's to do with the rheology of the fault zone, the properties of the clays and rocks in the fault zone. Why doesn't it work? Well, let's have a look at the next picture and I'll show you. Okay, the clue comes from the Sivrice earthquake. What you can see here is the aftershocks in blue over a period of 3 or 4 months, okay, following the earthquake. And you can see 2 curves. Afterslip starts again on the 21st of March, even though the main shock was in late January. Oh, yes, I think it was late January, the main shock. So the explanation why afterslip curves do not work is because aftershocks each introduce their own afterslip decay curve. It's very obvious here because a magnitude 5.1 earthquake close to the creep meter has restarted the afterslip process. Now, it doesn't mean you can't use this to determine rheology. It just means you've got to be very careful how you do it. Next. They really got any good afterslip curves yet, because in fact, the Sivrice one is probably the best one we have. Even that doesn't have the start. And what I'm showing here in the top right-hand graph is a logarithmic decay of afterslip following, shall we say, the Parkfield earthquake. On the left is the actual data, and on the right is afterslip with a logarithmic decay time scale. So it goes from 1 minute to 1 hour to 1 day to 1 month to 1 year. And I've numbered it 1, 2, 3, 4, 5, 6, 7. These are like octaves. As much slip occurs in the first octave, in the first minute, as occurs in the next 10 minutes, as occurs in the next 100 minutes. You get the idea? And the pink shaded region is the region where most creep meters have gone off scale. And the reason they've gone off scale is that creep meters, in order to pick up these very small movements, don't have much range. And we have managed to overcome that, the next slide, with a creep meter that has a huge range. It has a resolution of 2.5 microns and a range of 1.7 meters. You can see the carbon fiber rod that crosses the fault here. That pulls a little wire that's wrapped around a sensor here, and it goes around the shaft once, and then it's paid out by a spring on a wheel. And the idea is that the very high resolution comes from the rotation of this sensor here. One revolution is 10 millimeters, and the long range comes from the length of this very fine wire that's wrapped around the spring system. Next slide. Okay, so if we look at the logarithmic decay curve from Sivrice again, instead of looking at in time like we were just now, we look at it in log time, you see something pretty interesting. The graph here shows the main shock starting there and the aftershock, the 5.1 aftershock starting there. So now in log space, you've got an almost straight line for the first month of data following the earthquake. But what if we project the curve backwards in time to a millisecond or so after the earthquake? Well, it doesn't make sense to do it a millisecond because the earthquake propagates its rupture to the surface at about 3 meters per second, 3 kilometers per second. So starting a few seconds after the earthquake is good enough. And what you can see is that there's a dotted or dashed blue line, which shows what happened when we weren't there, before we arrived, before the surface started slipping. In other words, if we'd arrived at the time of the earthquake, we were standing on the fault during the earthquake, there would have been no slip at all. The slip starts in the subsurface and takes, and in this case, it took about 6 days to get to the surface. So this is a form of afterslip, but it's not anything we can see on the surface. So we'll have to call it something different. Virtual slip. It's real slip, but it's in the subsurface. Next. Okay, now what you've all been waiting for and what I should have been talking about, the earthquake measurements that we've just done in the last few months. So the Sivrice creep meter was operating during the earthquake. It registered only 1 millimeter of triggered slip, and it was probably a strain pulse from static strain from the earthquake. We then installed 13 extensometers. Most of them were new. There were 1 or 2 that we had to repair to keep going. And we had 3 extensometers running on the North Anatolian fault. I've already shown you those. 7 of them transmit data once per hour, and you can look at them at a public website if you want. 4 of them have to be collected because they're running on batteries. We didn't have enough transmitters. The resolution of them all is 2.5 microns. The range is 1.5 meters. The sampling rate is once per minute and the transmission rate once per hour. And we had 1 go wrong, which we've had to repair. Unfortunately, it was in an important place. So here we are. There is the rupture zone. Each triangle is a creep meter. They're named by the names you'll find on the website. Well, see, Balak Bono didn't get a name, but we're pointing out the displacement, co-seismic displacement in meters, and after slip that we've measured subsequently. And the striking thing is that there's hardly any after slip. This ruptured and almost stopped dead after that, with the exception that at Gazerne, the slip rate is currently about 12 millimeters a year. There's been 1 millimeter of slip we've measured. That should be 1 millimeter per week of slip, sorry. In other words, Gazerne, which is at the end of the rupture of this northern rupture, is in fact measuring continued slip on the fault, and that's evident from the after shocks that you can see. Next. So here's the data. I don't want to dwell on this. This is a horrible mess. Here, the pictures is very confusing, but I'll show the details in a minute. The aftershocks are shown at the bottom, the two main shocks, followed by a bunch of magnitude 5s and 4s and so on. And you can see the aftershock sequence was over very rapidly, and it's quite possible that we missed a lot of the after slip for the same reason. We just arrived too late. Next. Sorry, it's taking a while to load. I'm going to show you the I think it's this being slow. Okay, so here's the main Anatolian fault creep meters, and I'm showing the co-seismic slip and the Coulomb failure expectations calculated by Ross Stein at Temblor. This is basically a uniform slip model, so it's not very exact, but it illustrates the main thing. At Caracose, near the end of the rupture, we get a region of red, meaning that we should expect a lot of additional slip there. And to the south, we should expect slip because there was a slip deficit there. And so we put our instruments there. So this slide basically shows you why we put our instruments where we put them. And the next slide, you can see the same graph, same Coulomb picture for the northern rupture. And we only have 2 instruments on that, one at Goksun, the other at Gazerne. And we don't have a lot of data from Gazerne because we only put it in 3 days ago. But what we do see is at Gazerne, I'm showing the last month of data there, you can see 4 millimeters of slip, and the earthquake that happened a few days ago, 4.5, it triggered a half a millimeter of slip on the fault. And we can legitimately ask the question, is the creep rate there high because of subsurface slip, or is the surface slip actually indicating the strain rate, the high strain rate that's been generated by the slip on the fault? In other words, the two things are going hand in hand, the after slips and the after shocks. Somewhat to our surprise, at Gazerne, we only measured a millimeter a month of slip. Okay, which is, you know, it's unexpected because it's at the other end of the rupture, and we would have expected larger slip there. Okay, now last few slides show one of the most interesting things that we discovered. This is a releasing band near Caracose at the end of the rupture. The solid white line shows the fault in the bottom left-hand corner, and it shows the fault is offset by about 1.2 kilometers compared to the continuation of the fault to the north, on which we've not measured any rupture or after slip. But in between these two things, over a space of about 5 kilometers, you can see a series of ruptures. I've highlighted them with dashed white lines. And these ruptures are in tension. You can see the white arrows caused by the fault moving left lateral. The tension is opening the cracks and making it easier for them to slip, one would think. But the rupture has been unable to get past this subsurface structure, this offset, this restraining bend. It stopped it. What we measured was 30 centimeters of slip at the location where we installed the creep meter, the green triangle, and we noticed there's some very interesting geology going on. On the next slide, we'll show that the area is, in fact, it's that double red line on the left. Okay, it's a small graben on the hillside, and we put a creep meter there just 3 days ago. I'm showing you the data from it. It's not showing much at the moment. Just a few tens of microns of slip, but we expect that may grow over time. Of particular interest is that there is a large dilation signal. In other words, that graben is currently widening. Okay, if we look at, before I leave this, there is an exposure of the main fault in the quarry nearby, about 100 meters down the hill, and that shows a fault breccia, which is quite unusual. It shows blocks of rock, boulders measuring 10 to 40 centimeters in diameter, angular blocks that have been broken and split apart by the movement of the fault, that are cemented together by fluids coming up from below. The fluids coming up from below are, in fact, carbonates. So the rocks are cemented with carbonate, completely impossible to dig or without explosives, actually. It's that hard. And yet nearby, we're seeing faulting on a graben that's been pulled apart. Next slide. This shows a cross-section of the graben. Notice the hillside is dropped down to the right. So if you're walking up the hill, this fault would be a normal fault, and it would drop the hill in front of you about 50 centimeters. And the sinistral slip is occurring on one of the branches of the graben that we've measured. We put the creep meter both across the graben and along it, so we're measuring both components. And this structure has a very special name. It's called a sakongen, and it's usually only found in mountainous country that has recently been deglaciated. So this is quite an unexpected feature to find on the North Anatolian Fault. East Anatolian Fault, thanks. So last couple of slides. The Savrice earthquake didn't have very much surface slip. It had a small amount, around about 20 centimeters. And the slip that did occurred in the form of creep. And what we've noticed is this earthquake hasn't managed to breach the surface there either. So there's something special about the fault zone in the transition between the Sivrice earthquake and the recent earthquakes. And right now we're measuring accelerating slip. We've got a transmitter. The data are up to a few hours ago. And you can see that it's moving in a right lateral sense at Sivrice. The extraordinary thing that is that if you look at these graphs, let's look at this one here. This is a co-seismic displacement using spot 7 subpixel correlation. And you can see that the Ormanichi creep meter that was put on that branch of the fault should have experienced some slip. And when we went there, we found that there were cracks in the ground with evidence of slip of about 10 centimeters. So the Sivrice rupture was triggered again by this earthquake. It slipped a bit. Subsequently, let's look at this bottom right picture. This is post-seismic sentinel data from ASEA. And you can see now that subsurface creep has shifted to a different branch of the fault. In other words, the Ormanichi creep meter shouldn't be measuring anything, and it isn't. It's measuring, in fact, negative slip, collapse of fault zone features of some sort. And we haven't yet managed to identify where the creeping fault's going to make it to the surface. We've put in 3 creep meters there, and so far we haven't seen anything. The plan was to put in an array of creep meters over a 100-meter zone to try to identify where the creep was coming, and we failed because the fields are now being covered in wheat. The farmers are growing wheat there. Next slide. So almost the last picture. Sorry, this is a terrible computer. Okay, here we are. This is an exposure of the East Anatolian Fault, and you can see it's about 100 meters wide. It's got dark gray on the right. It's got light colored materials on the left. In between, there are browns and different shades of white. And we took some samples from what appeared to be the central portion of the creeping fault. And that's where we placed a creep meter above it there. And we took a sample back for analysis. The microscopic section on the bottom there shows a 75 microns for scale. And the gray blobs are lumps of quartz, that angular quartz that are rotated a little bit. It's a quartz schist. So the mica is the matrix that you can see deformed in between the quartz. Now, this rock was subjected to laboratory analysis, and it was discovered that when subjected to shear at room temperature, the material became harder and resisted slip. In other words, it's known as velocity strengthening, this material. And at increasing temperatures, the ability to strengthen became weaker and weaker. And at temperatures about 100 degrees, the opposite occurred. This quartz mica schist became velocity weakening. Okay, now the important thing about this is that at 100 degrees, you reach a depth of about 3 kilometers or something like that, given a standard geothermal gradient. And that means that this rock on the surface creeps, and at depth, it ruptures. Get it? This is what's causing the processes that we see at Sivrice. We are looking at a material that is just on the verge of becoming velocity strengthening above shallow depths. And it means that we do not see ruptures passing through the region between Tasmis and Sivrice. In fact, maybe the whole region between Karakoze and here is velocity weakening. So the slip is occurring at depth, and that is the end of my talk. I'm sorry we've gone over time, but if you've got any questions, I'd be happy to answer.
Hello. Anybody has any questions? You can just write them.
Or you may check the chat box as well. Sometimes they don't have microphones.
Here. Yes.
I have
Go ahead.
Go ahead, please.
First of all, I'd like to thank you as the head of the Department of Geometric Engineering here. So thanks for sharing your knowledge with us, especially with our young students. Thanks for conducting research in Turkey. And actually, I am more into Genesis. And I have really no questions, but I just want to ask one. So, as far as I understand, the 3 meter work is more because I saw those, 0.0 millimeters. So, when we are looking at, as Genesis persons, we might have 0.25, 4.35, especially in mid latitudes. The velocity uncertainty is different across the globe. In mid latitudes, we have more accurate velocity uncertainty, but at poles and at the equator, we have larger. So if we are lucky, we have something like 4.25. So I was just wondering whether you have noticed any bias in creep meter uncertainties or creep meter uncertainties and Genesis uncertainties. Although you mentioned about the complicated nature of these events.
No, I think I can answer that. First of all, GPS is not less accurate than creep meter. It's less precise. Precision, of course, is just the lowest digit you can rely on. So I think they both have the same accuracy. In other words, the values that you measure are important. And I think the thing that impressed me was that the GNS result from Ismet Pasha gives you 8 millimeters in 2 minutes. Ta-da! I can only give you 7 millimeters in 2 weeks. Now there's a discrepancy that puts them in a different class. In other words, we're measuring a different thing. Okay, you can't measure creep as it happens because it's happened so slowly. And you need a much higher precision. We have micron precision, you have millimeter precision. So it's a difference of 1,000 between GPS and GNS. Creep meter measurements. But I think creep meters are really complementary because they give you the time history of slip on the surface, something that you guys don't get.
Okay, so at the moment, there is no way of scaling Genesis measurements.
Well, you just can't get at microns, I'm afraid. But I think that doesn't matter. I think you can get the big picture, the larger scale wavelength things below the fault that we can't see. We're looking right on the fault. There are some things that are quite interesting. We can see the start of a creep event, for example. The first few minutes of a creep event is in fact the strain in the fault zone before the fault starts to slip. So there are things going on that is completely inaccessible to GPS, but we can't look below the surface. We can't tell you what's happening at 3 kilometer depth. That's what GPS is useful for.
Is there any other question here?
I think everything is very clearly explained.
Yeah, I think so. I have a question. What's for lunch?
We have many options.
Thank you very much for coming here and giving a nice
Yes,
talk.
Professor.
Really, thank you very
On
much.
behalf of my university,
And-
Graduate School of Science, we would like to thank you.
There is one.
Okay.
Did you say that the Sivrice earthquake and the Kahramanmaraş earthquake are similar in terms of creep character? So is there a creep in a similar character?
Okay, so yeah, the interesting thing is that there's a transition zone which stops both earthquakes. Sivrice couldn't move to the southwest, and the recent earthquakes could not move to the northeast. They were arrested by the creeping zone, which is strange. The creeping zone is just mud and, you know, schist rubbish. Why is it able to arrest earthquake rupture? Well, the answer is because it is velocity weakening. Okay, velocity strengthening. Once you try to shear the creeping zone, it resists. And we now know that there's a surface layer over most faults through sediments that prevents a rupture coming through to the surface, and it changes the whole nature of surface slip. Faults that ruptured to the surface in rock, like the recent earthquake ruptured right through rock through most of its passage, but where it hit deep sedimentary layers, the slip was less. That's also true in the Hatay end to the southwest of the main shock. So the thing that's common between Sivrice and the recent earthquakes is this creeping zone that stopped the rupture from propagating. And I think that gives us an interesting target to understand the rheology of what's going on the fault.
Quite an interesting situation. Thank you, they say. Okay. Is there any more questions?
If not, we would like to thank you, sir, on behalf of Graduate School of Science, and we have a little gift for you. I guess
A box.
Turkish coffee
Oh, really?
set.
Something in it.
And it
Oh,
is
no,
handmade
amazing.
because our
Oh,
university is
fantastic.
famous with that decorations,
Yes.
porcelain. So it's a
Oh,
coffee
wonderful.
set you enjoy with your
Thank
friends
you so
and
much.
family. Have a picture. Şey değil mi o? Aldın mı hocam? Yes. Teşekkürler. Çektin mi hocam? Thank you.
Thank you
That's
for the
wonderful.
attenders to